Hi, and welcome to this lesson on transmitters. In a previous lesson, we've discussed the elements of a radio link, including the elements of a transmitter. In this lesson, we want to do a slightly deeper dive on the topic of transmitters. First, we'll elaborate the various architectures that can be used for a radio transmitter, and there are many. Next, we'll talk about one of the most important things to know about transmitters, and that is the concept of a power amplifier. When we refer to something as a power amplifier, we are referring to something that has been designed to produce a specified amount of power at a specified efficiency. Power amplifiers are quite different from the linear amplifiers that are used elsewhere in a radio link, and I'll explain that. Finally, I'll introduce the concept of spectral regrowth, which is one of the naughty things that power amplifiers do. And I'll say a little bit about how that impacts spectrum management.
So, transmitter architectures. What I'm showing in this slide is the various ways that transmitters get implemented in modern radios, ranging from very simple methods to very sophisticated methods. Simplest methods being, for example, just using an oscillator and varying its magnitude and frequency, one or the other or both. And using just that much, you can generate AM, you can generate FM, you can generate a variety of modes, including digital modes like on-off keying. Or you could use a fixed oscillator and vary the magnitude of an amplifier. That's another way to accomplish amplitude modulation, used, by the way, in some applications. And then if we want to do more sophisticated things, it's easier to do it at lower frequency. So we can implement some kind of up conversion and then implement our modulator at baseband. We could use a direct conversion architecture. We can use a direct sampling approach with direct conversion. In other words, you can do IF sampling here and direct conversion here. Or we could do digital direct conversion. We could do everything in DSP at baseband, convert it up digitally, and then use a DAC to convert to the RF signal. Now, what's in common in all these architectures is a power amplifier, that final stage. And the purpose of a power amplifier is to deliver the power that we wish to apply to the antenna. Really, everything else in a transmitter is about waveform manipulation or shaping of the waveform. Where the power gets delivered is at the power amplifier, and that's really the defining characteristic of a power amplifier.
To understand what sets power amplifiers apart from most other amplifiers, we need to talk about efficiency. There are many ways to define and quantify efficiency, but the one I'm showing here is a pretty common one. In this definition, efficiency is the ratio of power delivered to the load, and typically that's the antenna, to the power that we must draw from the power supply in order to accomplish this. Now, to be clear, the efficiency of any practical amplifier is less than 1. That is, you normally can't output more power than you can draw from the power supply. One distinction between power amplifiers and other amplifiers is that the amounts of power are typically large, so you care more about how much power is being productively used. This is especially true since the power that is not productively used typically becomes heat, and that heat can be quite difficult to deal with when the power levels are high. It's probably easiest to see what's going on with an example. First, let me show you what is normally a bad way to design the output stages of a transmitter. Here we have two amplifiers. The first amplifier is a typical linear amplifier. Typically, but again not always, linear amplifiers are used only at low signal levels. So I'm referring to these as small signal amplifiers, abbreviated SSA. Now in this particular example, the first amplifier delivers 1 milliwatt output, and it requires 10 milliwatts from the power supply to do it. So, the efficiency of this first amplifier is, at best, 10%. And these are very typical numbers for a linear small signal amplifier. But maybe we require 1 watt of output from the entire transmitter. Well, in that case we need 30 dB of additional gain, and that has to come from this second amplifier. Now if we use the same linear amplifier technology, that means our efficiency remains 10%, and so the second amplifier will require 10 watts from the power supply. So, you can see two things right away. First, The power consumption is dominated by the second amplifier, which requires 1,000 times more power from the power supply. And this 10 watts that we're asking for from the power supply is a big ask, especially if the transmitter is something that is battery powered, and especially since we will need to somehow safely dissipate the 9 watts of power that are squandered in the process. The more common thing to do is to use a power amplifier in lieu of the second amplifier, and maybe also in lieu of the first amplifier as well. These days it is common to be able to achieve efficiency on the order of 70% or better, but only if you're willing to make some trade-offs. And one of these is being willing to fix the output power level to a specific value. Here we want 1 watt output, and not really a particular gain, so here the power amplifier makes sense. If we use a power amplifier with 70% efficiency, then we require only 1.43 watts from the power supply, which is an 86% reduction relative to what we needed before. If you're running this thing on batteries, that's going to greatly extend battery life. Also, there will be much less heat that has to be dissipated, and that will probably allow the device to be much smaller. So far, this is a big win. Of course, there is also a big downside in going this route, so let's call that out. To get 70% efficiency, the power amplifier will not be exactly linear. What that means is that you should expect that the waveform at the output of the power amplifier will be somewhat different from the waveform at the input. So let's address this aspect of power amplifiers in a little more detail. A truly linear amplifier is known as a Class A amplifier. Class A amplifiers require steady current, and they require that steady current even if the RF signal is 0, even if you're not transmitting anything. So, their efficiency is always less than 50%, sometimes by a lot. And that unused power has to do something, so it becomes heat. Therefore, Class A is not commonly used for power amplifiers, except for modulations that specifically require linearity. For example, amplitude modulation and single sideband modulation. Transmitters for those modulations may require the use of a linear amplifier, that is Class A, although there are ways to get around this even for those modulations. Modern power amplifiers are usually nonlinear, and they're labeled with a class of operations such as AB, B, C, D, E, and so on. These classes are all just different ways of being nonlinear. The key idea is that we're giving up linearity for efficiency. And to be clear, that loss of linearity usually means that the waveform will be mangled in some way that depends on the particular modulation and the class of the power amplifier. Fortunately, transmitter designers have become quite clever in managing this in a way that does not limit the performance of the modulation too much. Nevertheless, these consequences are significant. Broadly speaking, the two biggest problems are harmonics and spectral regrowth. Harmonics are simply weaker copies of the output signal which appear at integer multiples of the desired frequency. So, for example, a power amplifier designed to operate at 1 GHz will produce some output at 2 GHz and at 3 GHz and so on. These harmonic outputs can usually be suppressed using a filter. Spectral regrowth, on the other hand, is a somewhat more difficult problem. So let me say a little bit more about that. Here we're looking at the spectrum of the output of a power amplifier. The vertical grid lines are spaced at 5 MHz. In this case, the power amplifier is processing 2 signals simultaneously, which is pretty common. For example, power amplifiers and cellular base stations typically do this. Now, when these signals arrived at the input of the power amplifier, they were more or less completely contained within the vertical grid lines. That is, they were contained within 5 MHz of bandwidth each, with only a negligible amount of power going outside those limits. But the power amplifier is not linear, and that has resulted in some spreading of the power, and this has happened across at least 30 MHz of bandwidth in this example, whereas the original 2 signals together were limited to 10 MHz. This is an example of spectral regrowth. Note that the spreading of power will be a problem for a third signal that is either sent or received in one of the 5 MHz channels where this additional power has fallen. To deal with this, many power amplifiers use some form of linearization. That is, they remain fundamentally nonlinear, but there's some pre- or post-processing within the transmitter that's designed to reduce the spectral regrowth. What this plot is showing is how much less spectral regrowth is possible with this additional linearization step. So you can see quite a bit of improvement is possible, albeit with significant additional complexity, and you can never really completely eliminate this effect. Okay, time to review. First, you saw a brief summary of the various types of transmitter architectures, and there are many. However, each one of these architectures has a power amplifier as the final stage before the antenna. The purpose of a power amplifier is to produce a certain level of power at a certain efficiency. And to be clear, the goal of a power amplifier is not to provide a specified level of gain, nor is it necessarily to provide linear amplification. Finally, we talked about the consequences of power amplifier nonlinearity, especially with respect to spectrum management. The two big issues for spectrum management are harmonics, which can usually be filtered to some extent, and spectral regrowth, which makes it harder to put signals close together in frequency. That concludes this lesson on transmitters. Thanks for listening.